Okay, let's jump right in. You've brought us some really fascinating sources today. We're doing a deep dive into decoding speech straight from brain activity
Yeah.
using AI and, crucially, non-invasive EEG.
Yeah, it really does sound like something out of science fiction, doesn't it?
Yeah.
But these sources, they lay out the current reality quite
Yeah.
clearly. You know, the science behind it, the tech involved,
Right.
how they actually process the data, the role AI is playing, and importantly, the pretty significant hurdles that are still there.
Exactly. So our mission really is to explore these sources together, trying to understand how this amazing technology actually works, see what the data says is possible right now, and be honest about what still needs figuring out.
And one thing the sources hammer home right
Yeah.
away is the core challenge. It's less about just finding a signal from the brain
Mm-hmm.
and more about finding the right signal. Those specific electrical whispers linked to what someone intends to say.
Mm-hmm.
And they're buried deep in just a massive amount of noise.
That signal versus noise problem, it feels like the absolute foundation here, reading through this material. What does that noise actually, consist of? Why is it so incredibly hard to pull out the signal you want?
Oh, it's a huge mess, to be frank. The electrical signals we're actually after, the speech intention ones, they are incredibly faint. We're talking microvolts, just
Yeah.
tiny, tiny fluctuations.
Wow.
And they're happening while the brain is doing a million other things that have absolutely nothing to do with speech. Just, being conscious, other thoughts, background processing,
So the brain's just constantly buzzing with activity.
constantly. And then, layered on top of that, you've got physical movements. Even something really small, like you blink your eyes,
Mm-hmm.
or you swallow, or maybe tense your jaw slightly.
Mm-hmm.
Those actions create electrical signals, artifacts, that are enormous compared to those tiny speech signals we want.
Right.
Plus, just electrical interference from equipment, lights, whatever's in the environment.
Okay, so it really sounds like trying to hear someone whispering across a crowded room during like a thunderstorm.
That's not a bad analogy. The sources use one I really like. They say the AI needs to be a masterful detective
Hmm.
to find these meaningful whispers of intention within what they call a cacophony of biological and environmental noise. Think trying to pick out one specific word whispered during a loud concert. That's kind of the scale of the challenge.
Okay, that paints a very clear picture.
Hmm.
So, given that level of noise, the sources do mention there are different ways to look at brain activity, different neuroimaging tools. Why the focus on EEG here for this speech decoding task?
Well, yeah, other methods exist, like fMRI or invasive electrodes, and they have their place. But the sources really zero in on EEG for some very practical reasons. The main advantages they list boil down to accessibility and convenience.
Okay.
And crucially, it's non-invasive. You don't need brain surgery to put electrodes inside someone's skull.
Which is obviously a massive barrier removed if you're thinking about wider use.
A huge one.
Yeah.
But the sources are also upfront about EEG's downsides.
Right.
And you can immediately see how these tie straight back into that noise problem we were just talking about.
Right.
They imply, generally lower signal quality, maybe poor spatial resolution, meaning it's harder to tell exactly where in the brain the signal is coming from compared to those more invasive methods.
So it's a trade-off.
Definitely a trade-off. You get the non-invasive approach, which is great,
Hmm.
but you potentially lose some signal clarity or precision. Makes that detective work even harder for the AI.
Okay, so you managed to capture this incredibly noisy, faint signal with an EEG cap. It sounds like, based on the sources, you can't just feed that raw jumble directly to an AI and hope for the best. There's this essential processing gauntlet.
That's exactly it. The raw EEG data, which is basically just, messy multi-channel electrical readings changing over time, is pretty useless for decoding speech intent as is. So this multi-step processing pipeline they describe, it's absolutely critical. It's the cleanup crew, essentially, transforming those raw brainwaves into something structured that the AI can actually make sense of.
So what does that pipeline involve? What are the key steps they mention?
Okay, so it starts, obviously, with the raw EEG data, that messy stuff.
Mhm.
Then it goes into pre-processing. This is your basic cleanup stage. You're filtering out frequencies you don't want, like electrical hum. And really importantly, artifact removal.
Getting rid of the blinks and jaw clenches.
Exactly. The sources mention specific techniques like ICA, independent component analysis, which is basically a computational method to try and separate those big muscle signals from the smaller brain signals you're actually interested in.
Like digitally scrubbing out the concert noise.
That's a good way to think about it. And also segmentation, breaking up that continuous stream of EEG data into smaller chunks that might correspond to a word or a thought. Once it's cleaner, it moves to feature engineering. This is where you take the cleaned up data and transform it into a format that really highlights the patterns the AI needs to find.
How do they actually do that? Is it just looking at the squiggly lines over time?
Well, that's where one of the really key innovations highlighted in the sources comes in. They talk about creating 2D topographic brain maps.
Maps.
Yeah, think of it like this. You take the electrical activity measured by all the electrodes across the scalp at a specific moment or over a short time window, and you project it onto a 2D image, kind of like a heat map showing activity hotspots on the head.
Huh. Interesting.
They also extract more traditional features, like looking at different frequency bands, alpha, beta, gamma waves, that sort of thing, and how they change over time. But this spatial mapping into a 2D image is a big deal.
So you're turning these complex electrical patterns across the scalp into something that looks, well, more like a picture. Why is that helpful?
That's the clever bit. It reframes the whole problem. By turning the EEG data into these 2D maps, they can suddenly use really powerful AI algorithms that were originally developed for computer vision for recognizing patterns in images.
Ah, like convolutional neural networks, CNNs.
Exactly. CNNs are incredibly good at finding spatial patterns in images, identifying edges, shapes, textures. And by feeding them these brain maps, researchers can leverage that power to find the subtle spatial and temporal patterns in brain activity related to speech.
Okay, so you're essentially giving the AI a kind of brain picture to analyze instead of just a stream of numbers. And the final output of this whole pipeline is the AI model input clean, structured data ready for the actual decoding.
Precisely. And then comes the AI model itself. That's the engine that actually tries to make the leap from these processed brain patterns to words or text.
And the sources suggest there's been quite an evolution in the types of AI being used for this.
Oh, definitely. The field has moved really fast.
Yeah.
It started maybe with simpler machine learning classifiers that could just distinguish between a few predefined thought patterns or words.
Okay.
But the clear trend, as shown in the sources, is towards much more complex deep learning architectures. Those CNNs we mentioned, or models like RNNs and transformers, that are specifically designed to handle sequences of data, which is obviously crucial for language.
And does all that extra complexity actually translate into better results? Better decoding?
According to the data presented in the sources, yes, absolutely. The trend they illustrate is pretty clear. As the models get more complex, and this is important, as they get trained on larger amounts of data,
Right, data is key.
their performance improves significantly. They become better at handling larger sets of possible words, larger vocabularies, and generating output that's more, coherent, more like actual language. These deeper models can automatically learn subtle, complex features from that noisy EEG data that simpler models might miss, and they're better at understanding the whole sequence, the flow of language.
Okay, so that naturally leads us to performance. What does the state of the art really look like today based on the benchmarks the sources provide? How good are these systems actually?
It's kind of a mixed picture. There were some really impressive breakthroughs, but also some very clear limitations still. The sources give a couple of key benchmarks to illustrate this.
Yeah.
One is a recent result from a model called D-Wave. It used non-invasive EEG to translate text that people were reading silently in their head.
Silently reading, okay.
And it achieved a BLEU-1 score around 40%.
40%. Now, for translation tasks, a BLEU score of 40, especially BLEU-1, which just looks at single words, it doesn't sound amazing, does it? Like,
Yeah.
not fluent translation.
No, it's definitely not perfect fluent translation. You're right. BLEU-1 basically measures how many individual words in the AI's output match the original text. But what that 40% does show, and why it's significant, is progress in what they call open vocabulary generation.
Meaning, it wasn't just picking from a small list.
Exactly. The AI was attempting to generate text more freely, not just classify into a few known categories.
Yeah.
So while the accuracy number itself might seem modest compared to, say, machine translation between languages, achieving that level on this task from noisy EEG is actually a pretty big step forward in tackling the complexity.
Okay, so genuine progress on generating text from silent reading, even if it's, well, still a ways off perfection. What was the other main benchmark they mentioned?
The other one focused on imagined speech. So someone thinking about saying specific words but not actually moving their mouth or vocal cords.
Right.
And here, a different system achieved a much higher accuracy, 91.2% word recognition accuracy. This was specifically for decoding synthesized Chinese words from imagined speech EEG.
Whoa, 91.2%. That sounds incredibly high.
It is very high, and it proves a really important point. The sources say it shows that intelligible audio can be generated from EEG. It demonstrates the potential to create audible speech just from thought, basically.
But there's a catch, I assume.
Well, the key difference is context. That 91.2% was achieved when recognizing words from a known limited set. It's really good at telling which of those specific Chinese words the person was thinking. But that's a different, arguably easier task than freely generating any word in response to spontaneous thought, like in a normal conversation.
And that difference seems to be exactly what the sources call the vocabulary challenge. It sounds like this is the major bottleneck for making this truly practical.
This is probably the biggest reality check presented in the sources, yeah. They show data, often in charts, demonstrating that while accuracy can be really high when the system only needs to tell apart a few words, say, distinguishing up from down or left from right, that accuracy drops dramatically as vocabulary size increases.
So the more possible words the AI has to choose from, the harder it gets and the more mistakes it makes.
Precisely. This fundamental limitation, which the data clearly shows, is what makes that dream of true conversational AI, decoding spontaneous, free-flowing, natural speech directly from brainwaves, such a difficult goal right now.
It makes intuitive sense.
Yeah. It's one thing to train a system to recognize, say, 10 specific command words with high accuracy in a controlled lab setting. That's achievable now. But it's a completely different ballgame to decode any word someone might think of, from the tens of thousands of words we use in everyday language in real time in any context. That's much, much harder.
So, okay, we've seen impressive progress, proofs of concept, high accuracy in limited scenarios. But decoding natural conversation is still a huge mountain to climb.
Absolutely. And the sources are quite clear about the major hurdles still remaining before we see practical brain-computer interfaces for communication being used widely outside of specialized research labs.
What are those key challenges they highlight?
Well, first there's the data bottleneck. We touched on this. But these complex, deep learning models, they are data hungry. They need massive amounts of high-quality, precisely labeled EEG data to train effectively.
And getting that data is hard.
Incredibly hard. You need reliable brain signals, accurately time-locked to specific words or thoughts. Collecting that from many people over long periods is really difficult, expensive, and time-consuming.
Just getting enough good brain training data is a fundamental issue.
It really is. Then there's the problem of generalizability. This is a big one. A model trained really well on one person's unique brain patterns often performs poorly on someone else. Sometimes it doesn't work at all.
Right.
Or it might not even work reliably for the same person if you test them on a different day, or if they're tired or stressed. Their brain state changes slightly.
So the models aren't robust.
They need to become much more robust, much more adaptable across different people in different conditions, different times, making the technology work reliably for anyone, anytime. That's a major challenge.
Makes sense. What else?
Hardware miniaturization. This is more on the practical engineering side, but it's crucial. For these systems to leave the lab and be usable in daily life, the hardware, the EEG caps, the amplifiers, the processors needs to get way smaller, more comfortable, less obtrusive than the bulky setups used in research today.
Yeah, you can't expect people to walk around wearing elaborate EEG helmets just to communicate.
Not realistically, no. And finally, perhaps the most profound challenge the sources raise: ethics and privacy.
Right. This must come up.
Absolutely. As this technology gets better, even approaching the ability to decode thoughts or intentions, well, it raises huge questions. Questions about consent, truly informed consent, about the security and ownership of incredibly sensitive brain data, the potential for misuse, surveillance manipulation. These are massive ethical considerations.
These aren't just technical problems, they're fundamental societal questions we need to grapple with as the tech develops.
Exactly. And the sources rightly highlight that these ethical frameworks and safeguards need to be developed right alongside the technology, not as an afterthought.
Okay, so wrapping this up, looking back over this deep dive through the sources, it feels like quite a journey. We started with that core challenge, finding the tiny speech signal amidst all the brain noise. We walked through that essential, really complex processing pipeline needed just to clean the data up.
Yeah, turning raw waves into something usable.
We saw how AI, especially deep learning, has evolved to become the engine trying to make sense of it all.
Constantly getting more sophisticated.
Then we looked at the actual performance, those benchmarks showing, exciting potential, like that high accuracy on limited words, but also hitting that very real vocabulary wall.
Right, the gap between limited tasks and real conversation.
And finally, outlining those significant hurdles still ahead. The data problem, making it work for everyone, shrinking the hardware, and navigating those crucial ethical questions.
It really does paint a picture of a field with just incredible potential. The hope it offers for restoring communication for people who've lost their voice is profound.
Absolutely.
But it's also a field that, as these sources make very clear, requires a massive amount of continued scientific effort, engineering innovation, and very careful ethical thought.
It definitely gives you, the listener, a much more nuanced perspective, I think. You can appreciate the sheer cleverness of the breakthroughs that have been made,
Yep.
while also understanding the enormous scale of the challenges that still need to be overcome. It makes you think, doesn't it? Considering that vocabulary challenge specifically, what's the fundamental difference between decoding, say, 1 of 10 intended words versus capturing the sheer spontaneous complexity of how you think or talk every day? Is it just a matter of scale, or is it a different kind of problem altogether?
That's a really interesting question to ponder. And it ties back into those ethical concerns, too. As these technologies inch closer, even if full mind reading is distant, what does it mean for us, for society, when we start potentially accessing and decoding even fragments of that internal private monologue? It's definitely something to keep thinking about.